and a very good afternoon to all of you. On behalf of Keysight and on behalf of myself, I sincerely thank you for attending the talk and honored to be here to present it. I feel a certain responsibility as the very first speaker of the session. We are here today to talk about AI and the role of AI in 6G in general, but also talk about AI from the perspective of Keysight, since this is a vendor perspective session as well. So let's begin with a little bit of the basics. The term AI has been used a lot, there are many flavors and many concepts that are underlying the term. There are at least three distinct things that we talk about when we say AI or AI ML in general. There is machine learning, that is basically an algorithmic approach to learning from data. And there are layers underneath it and layers above it. When we talk about deep learning, again, it is also something that machine learning can do, but it has to do with very large amounts of data and certain specific types of networks that are used for learning. But then when we talk about artificial intelligence as a whole, what are we talking about? It is the overall, the concept of a program or a piece of software understanding intent and applying that intent to solving a specific problem in a way that human intelligence may approach that problem. And of course, it's a very broad definition, and in some places, controversial definitions still emerging as well. And AI ML, as you know, has pervaded the entire space, not just this industry, but almost every industry all around us. And in fact, telecommunications may be one of the more recent or last areas where it may be pervading. And it is useful for us to both analyze the evolution of AI ML and its entry into other industry segments, let's say like the pharmaceuticals or like in energy and so on and so forth, to understand the shape that it will take in telecommunications as well. So again, a little bit more about AI ML. When we talk about using AI ML to solve a problem, what exactly do we mean, and what are the pillars of an AI ML solution? We see there are three main pillars. One is what is the type of learning, and this is really a function of the type of data that's available, and also the source of the data and the location of the data, or locations of the data, and so on. There can be supervised learning where a desired outcome, and you are able to compare that with the outcome generated by the machine learning model. Unsupervised learning is where you don't have such immediate feedback, and so on and so forth. And then federated learning, for example, is learning across multiple geographically or otherwise logically distributed modules. That is one pillar. Then the second is, what is the type of outcome that we are attempting to obtain from this particular AI ML solution? Are we trying to predict something? Are we trying to classify something? Are we trying to detect anomalies or patterns in a certain set of data? Or are we actually trying to understand real-world language or real-world human interaction or gestures? Or are we trying to learn from a huge set of documentation to provide certain essential recommendations out of it, or even abstracts of the learning, so on and so forth? And then finally, are we actually trying to generate data that looks like what the machine learning model was previously fed, or looks realistic, or looks, or basically satisfies certain constraints. A poem that looks like it was written by Shakespeare, for example, is an example of generative AI. So that's another pillar. What are we trying to achieve? And finally, the nuts and bolts of AI, algorithms themselves. What are the types of models that are needed to achieve these outcomes using these learnings? Again, this is an area of ongoing research and explosive research, I would say. And over the past decade or more, a tremendous number of advances have been made. We started off with just what we used to call convolutional neural networks, CNNs, but over time, autoencoders and transformers, and then generative, AI, GAN networks, for example, and then diffusion models, so on and so forth, have now pervaded the space, and each of them have very specific types of intent and a specific type of application, and it's suitable for specific problem solving. And these all are sort of the three basic pillars of how you would use AI/ML to solve a problem. Again, a few words about the history. In the 2000s, we were doing very simple tasks with AI/ML, like, let's say, search engine optimization or mapping, for example, and some very simple types of language translations. But then, in the 2010s, you had more and more complex algorithms and algorithmic methods and programming languages like TensorFlow, like PyTorch. They helped kickstart this movement, and you had more and more complex programs like Siri and Alexa and the IBM Watson and AlphaGo, for example. These are all examples of much more complicated solutions that really wowed the industry or the world as a whole and captured the imagination. And then finally, in the 2020s, which is what we are living through now, we of course have ChatGPT, and then Llama and Gemini and all of the more recent incarnations, which are really pushing this AI into the masses, into many of the industries, replacing coding for achieving many of the tasks, and so on and so forth. And of course, in the middle of all this, us as the telecommunication industry are also trying to embrace AI/ML and trying to understand where it can be inserted and where it can be used. Of course, there has already been use of AI, let's say, in the back end, in terms of analytics, in terms of even customer relationships and so on and so forth. But now there is more and more movement towards using AI in the radio access network, in the core network, in the application space, and so on and so forth. Along with all of this movement towards AI is also a lot of concern about AI, and also a lot of, let's say, legal work in AI. The European Union AI Act is one example, and in the US there is a forum to talk about AI security that is led by NIST, and across the globe there are various such examples. So the policy-making world is slowly also gearing up for what will become one of the important pillars of the next generation of telecommunication. So shifting into wireless communication, on the left here you see what is quote-unquote the conventional or traditional network, with the physical layer, the modulation, coding, and then the MAC layer on top, including things like scheduling, things like beamforming, and then one more layer on top for radio resource management, mobility, and what used to be called self-organizing networks, or SON. Now we are moving into an AI-powered network paradigm where we are talking about an AI-designed, dynamically adjusted physical layer, the modulation and coding combined, and the beamforming and so on, done in a way to fit the exact channel in the exact environment that it's deployed in on a very dynamic basis, going well beyond the conventional 3GPP methodology of picking 1 out of 29 MCS schemes, which is what we do today. Then, moving further up the chain, or up the stack, that is, we are talking about using, AI both in the close to the radio as well as in the edge and in the cloud, in order to provide advanced intelligence for scheduling, for beam management, for mobility, and so on and so forth. And the open interfaces like the RIC interface that was created in ORAN has also enabled a faster movement towards this paradigm by enabling entities and companies with knowledge of AI, but not necessarily knowledge of the wireless, and different kinds of players to interact with each other in this domain convergence that's happening. And even beyond the radio access network itself, we are talking about the whole life cycle of the telecommunication network, including network planning, including continuous integration and continuous deployment pipelines. All of these are being impacted by the use of ML. So this is where the industry is shifting towards. I talked in the previous slide, so I'll be very brief. It's simply a reiteration of the physical layer going from the current current status to an AI designed and AI native one in future. So why is AI so complex? I mean, why is AI so necessary? It has to do with the complexity of the network that is simply as we are adding more and more spectrum, as we are adding more and more channels, as we are adding more and more to the demand and to the types of applications that we want to support and the type of use cases that we want to support, the dimensionality of the overall problem that we're trying to solve has simply grown to an extent that a conventional algorithmic, or heuristic mechanisms to solve these are no longer sufficient to provide global optimality and improvement in efficiencies. And that is the reason that we need AI in 6G. And there are many opportunities for AI in terms of RAN performance. In terms of core, when we talk about RAN performance, we talked about, already about beamforming and beam management, which are being currently talked about in 3GPP. But beyond that, also as we go towards, extreme massive MIMO, and further use cases beyond in terms of very hyper accurate positioning, for example, these are all areas where ML is certainly a candidate. And then when we move to core network, we can talk about capacity, about slicing, about service, service-based architecture and how that impacts the performance of the network as a whole. And of course, analytics, again, there is a huge impact in terms of identifying and reacting to discrepancies, but also preventing them in a predictive manner. And ML has a huge role to play in it. But ultimately, the question becomes, where are the sweet spots? Right? So there is some hype, there is some reality. Ultimately, the usage of machine learning will have to satisfy a combination of a lot of different elements. One is, does it yield better results than the current state of the art? In some cases, it does. And in some cases, there is still feeling that we have to go beyond the current status in terms of the computational power that we may have or the efficiency that we may have before we start seeing results with ML, because the dimensionality of the data that's needed for training that ML may be too high by itself. But also, does it cost less, or at least comparable to what we have today in terms of compute power? Does it consume less energy? So if you create a highly efficient wireless system, but it consumes more power in order to do the data training in the back end in compute farms, then you have kind of lost that battle already. All of these things have to fall in place. And finally, most importantly, the policy guidelines that are coming from the various governmental bodies, from the standards bodies, in terms of the incorporation of the AI, in terms of the security, in terms of safety and quality assurance, in terms of protection against catastrophic outcomes. All of these need to be taken into account, and only then you will have successful adoption of AI ML. There are many challenges along the way, I would say. Right now, the biggest one is insufficient training data in general. Right? So training, the real world data has lots of privacy concerns attached with it that's not easy to scrub and use for training. So we also try to rely on synthetic data. We are increasingly working in an open environment with lots of different vendors, lots of different interfaces, and AI actually across lots of different these boundaries. And so cooperation, model sharing, all of these things become important. How to ensure proprietary and value addedness in individual vendor solutions, while at the same time conforming to an end-to-end interoperable efficiency. I think that's a key question that we have to do. And testing and validation of AI is a huge area that has to be addressed. And I have maybe a slide coming up on that. And finally, creating models that are general enough and models that are not overtrained for very specific circumstances, but then fail when they're deployed in a much more generalized environment. The entire life cycle of AI ML has to be taken into account when we are talking about testing and validation. We have been operating in a certain type of test and evaluation paradigm now, where we know specifically, there are very clear specifications written, so for interfaces, and for functionality, and there are very specific types of testing that you can do in order to achieve those, like conformance testing, interoperability testing, and performance testing, and so on. But with the advent of AI and the dynamism that it incorporates, a lot of these things change. And so you have to look at all of the steps of the AI ML life cycle and look at how exactly continuous testing and validation can be done across all of these. And these include all the way from the data analysis for the training data to the validation of the model in training, to when and how do you redeploy or retrain the model, and how do you monitor the performance over time. So coming to Keysight, we of course are one of the major players in the test and measurement world, and we are approaching AI ML with all of the seriousness that it requires. We are major participants in all of the standards bodies and alliances, the 3GPP, ORAN, NextG Alliance, the FCC, Technical Advisory Council, AI-RAN Alliance, and so on and so forth. We are looking at this problem from all angles. I just want to present a few examples of some of the practical things that we have done in the very recent past. What we are showing here is a test bench to test the AI air interface. This was done as part of an EU project called the 6G Sandbox and also Centric. And basically it involves testing a neural receiver from NVIDIA using our end-to-end test bench that is shown here, including signal generator, channel generator, and a commercial radio ORU, and then our DU receiver emulation. That's one example. Another is our active role in 3GPP standardization. We are very much, in the forefront in terms of driving test methodology for AI/ML. Right now, the hot topic is beam, the beam optimization problem in AI/ML that's currently being worked on, along with positioning and a couple of others. This is examples of the types of work that we do, not just in terms of the results of the system itself, but how will you evaluate it, what kind of over-the-air test mechanisms do you need, what is the complexity of those, and what are the trade-offs that have to be made in order to make the complexity manageable. And another example, AI will pervade, as I said, all aspects of telco. And one example here, which is, relates to the new emerging use case, is sensing. What we are showing here is a test setup to do joint communication and sensing, and the specific problem we are showing here is gesture recognition. We had a robotic head mimic yes and no, based on our sensing signal, and then an ML algorithm on the sensing signal, we show whether that gesture can be recognized correctly or not. So this is an example of how evaluation of these ML algorithms requires a lot of things, including the hardware setups and the correct form of signal collection and data collection that go with the ML methodology that comes on the other side. And sensing is a vast topic. We have so many different variations of it, very different use cases, whether it's outdoor or with mobility, or it's indoor factory environment, or whether is it with in the FR3 band or FR1 or FR2. It has very different implications in terms of the sensitivity, in terms of the the range it can obtain, and in terms of the resolution it can obtain, and what it can recognize, and so on. So it's still an area very much being experimented on and understood. One last thing I want to emphasize the role of digital twins, which we think are very key. A lot of times, these AI/ML algorithms are written for very large networks, optimization problems, and it's really not possible to experiment with a real-world large network, and you need a digital twin of the network in order to provide a safe sandbox in order to experiment with AI/ML algorithms. So it's a very essential part of the AI/ML strategy for the industry as a whole, and for Keysight as well. I think I'll stop with that. There is one more I wanted to mention in terms of the AI is not just about optimizing the network itself, but there is also another opportunity to use AI/ML modeling in the digital twins themselves. So that's the last point I wanted to make. With that, I'll basically wind up the talk, and just to say that as you can see, it's not possible to bring out the full complexity of the use of AI/ML in 6G in a short talk like this, but hopefully I give you a good.
Yeah, thank you for presentation.